Welcome to the video lecture on More with Matrices in the Calculator. We're going to start by reviewing a little bit about how to use matrices to solve a system and what can happen in various cases for solving systems. First of all, an equation of the form ax plus by is equal to c is called linear since its graph is a line. For a system of linear equations, exactly one of the following is true. Either the system has exactly one solution, in which case you would see a graph that has two lines crossing and intersecting at exactly one point. Such a system is said to be consistent. That means it has a solution and it's independent. Another possible case is that the system might have no solutions at all, and that's going to happen when you have two lines that are parallel, so they never intersect, they have no points in common. We say that such a system is inconsistent, and that's the word you use whenever there's no solution, and it's also considered independent as well. The third possibility is when your two linear equations turn out to be exactly the same line. So that would be the case of having coinciding lines, one line right on top of the other. And so your solution is going to be every single point that lies on that line. So there's an infinite number of solutions, every point on the line. We say that such a system is consistent because it does have a solution, but we say that it is dependent because the solution depends on the equation of the line. So in a system where you're talking about linear equations, typically a 2x2 system, these are the three cases that might happen, and it's easy to sort of visualize those geometrically by just thinking about the graphs of the lines. However, it's a lot more difficult to visualize if we have 3x3 systems or n×n systems where you have n equations and n variables. The statements are still true in those bigger systems. Now, before we move on to an example, let me pull up a PDF that shows a copy of something straight out of the textbook of what it would look like to see 3x3 systems graphed. And when you graph a 3x3 system with an x, a y, and a z, instead of having graphs that look like lines, these are actually planes. So you can see the different cases here as well. In this first case, you have all three planes, all three equations intersecting in exactly one solution, and we say that it's consistent. In the second case here, there's actually two possibilities where you have also a consistent system, but this is where they intersect in more than just a point. In this case here, it intersects in a line, and in this case here, all three planes turn out to be the same plane, so they would be coinciding planes. And so it's still considered consistent, but it's also dependent on the equations. The last case here is your inconsistent system, kind of like our parallel lines. Here we have parallel planes, and since these never intersect, you have no solution. And this case here is similar in that you have two planes intersecting, but not all three planes at exactly the same place. So this would also be considered inconsistent. Okay, let's take a look at an example. In solving a system of equations, we are attempting to find a solution by creating an equivalent system whose solutions are more obvious for us to see. An equivalent system is a system whose solutions are the same as the original system. If we're using our elimination method, where we try to eliminate x's or eliminate y's, then there are three steps or three operations that can be used to create an equivalent system. The first one here is sort of the tricky one, and this is where you take an entire equation and multiply it by a non-zero number, and then add that result to another equation. And this is kind of what we do when we're multiplying an entire equation by a constant to get that coefficient to be opposite, and then we add our two equations together to cancel out those x's. The second operation here is a little bit simpler. Here all we're doing is multiplying an entire equation by a constant. And the third operation we're allowed to do is to just interchange the position of two equations. It shouldn't matter which equation is on top, so you can switch back and forth. So let's solve each of the following systems. So this is just kind of review on these three problems. This is stuff hopefully that you already know how to do. So on this first system here, what I could do is use elimination to get these x's to cancel out. And because they're already both have coefficients of positive 1s, I would like one of these to be opposite. So I'm just going to go ahead and multiply this second equation through by a negative. I'm not going to do anything to that top equation, leaving it the same, but the second equation becomes a minus x, a minus 4y, and a negative 13. And now when I add the two together, so this is that step 1, that operation 1 where you both multiply and add, these x's now cancel out. And we're left with negative 7y equals negative 21. Divide through by negative 7, and that tells me that y is 3. Now in order to find x, I need to take that 3 and plug it into any of these equations. And I'm just going to go ahead and use this second one here and substitute in 3 for this y. It doesn't matter which equation you use. 4 plus 3 is 12, so when I subtract 12 over to the other side, we get x is 1. So our solution is 1, 3. And this would be the case of graphing these two lines and finding out that they intersect at the point 1, 3. Now let's take a look at this next example. Here we want to do something similar. Let's try to eliminate our x's again. This time our bottom equation has a 2, so I would like this top equation to have a minus 2 in front of that x. To keep it balanced, I have to multiply the entire top equation by minus 2 so that it stays equivalent to what we started with. So it's going to turn into a negative 2x, positive 6y equals 16. Line up the second equation underneath, not doing anything to it, and now we're ready to add these two together so that the x terms cancel out. Notice also that the y's cancel out. So what's left over here on the left side of the equation? Since all the x's are gone and all the y's are gone, we're just left with a 0 on that left side. Now look at the right side. 16 plus 12 is 28. Does 0 equal to 28? No, that's a false statement. So what's going on here is we have two parallel lines. Whenever you have two lines that never intersect, you're going to get this false statement. So this is going to have no solution. Or you could just write 0 with a slash through it. Okay, let's take a look at the last example here. Doing the same exact thing, trying to eliminate the x's by multiplying through by a negative 2. This top equation becomes negative 2x plus 6y equals negative 16. The bottom equation I'm going to leave it the same and line it up underneath. And now when I go to add these together, the x's cancel and the y's cancel, so I have a 0 on the left side. But this time the constants cancel as well, so I have a 0 on the right side as well. And now this is a true statement. What that means is that these are two coinciding lines. If you were to graph them, they are exactly the same equation. In fact, if you take this second equation and divide it through by 2, you'll get exactly that top equation. So it's just two different forms of the same line. Now, how do you write your answer when it's coinciding lines like this? Your answer is not all real numbers. Your answer should be all the points that lie on the line. When these two lines intersect, what they're intersecting in is just the points on the line. So we use kind of this fancy notation, a curly brace, and then we do parentheses x comma y with a colon, or sometimes you see a vertical bar there, and then you just copy down one of the equations in your system. It doesn't matter which one, because remember, they're the same equation. And what this is really saying is that our answer is all the points x comma y that satisfy this equation. So I'm only listing the points that are on that line itself, and that would be your final answer. Now we're going to talk about how to get our systems into special forms. So we say that a system is said to be in triangular form if the second equation does not contain the first variable and the third equation does not contain either the first or second variable, etc. The following is an example of a system in triangular form. So you can kind of see that triangle shape. We've got this diagonal with an x, a y, and a z. And in this bottom equation, there's no y's and no x's. In the second equation, there's no x's, but there's a y and a z. And in the third equation, we have all three. So this should look vaguely familiar if you've ever learned about how to use matrices to solve systems. And that's what we're going to eventually be talking about in this lecture. The reason we like this triangular form is because it makes it very easy to solve the system by using back substitution. Because right here from this bottom equation we can see that z must be 4, and then all I would have to do is then back up to the next highest equation, substitute in 4 for that z, and that tells me that y minus 20 equals 16, add 20 to the other side, and now we know that y is 36. And then you could back up to this top equation, substitute in 36 for the y and 4 for the z, and proceed to solve for x. So it makes it much easier to solve a system for the x, the y, and the z if it's in this triangular form. What our goal is to change a system of linear equations into an equivalent system that's in this triangular form. And the process of doing that is called Gaussian elimination, named after a famous mathematician named Gauss. Now we can do this by taking our systems of equations and turning them into a rectangular array of numbers called a matrix. Now the plural of matrix is matrices, and matrices are useful because they provide us with an efficient way of solving a system of linear equations. And you can also use your calculator to help solve these matrices very, very quickly. We say that an m by n matrix is an array of m rows and n columns. So this first number is always the number of rows in your matrix, and the second number is always the number of columns in your matrix. So this has m rows going across and n columns going down. When you see the subscripts on here, when you see something like a sub ij, that means that this is the element in this matrix that is in the ith row, because you always do the rows first, and in the jth column. That sounds kind of funny, but that's what the I and the J stand for. So the I that comes first is always telling you which row you're in, and the J is always telling you which column you're in. So you put them together, and that will tell you exactly one element in this matrix. Now we write a system of linear equations in matrix form by writing only the coefficients and constants that appear in the equations. We leave out all of the variables. The resulting matrix is called the augmented matrix for the system. So for example, if you look at this system of equations right here, if you strip away the x's, the y's, and the z's, it turns into a 1, -3, 3, 4. So this whole top row comes from the coefficients in this first equation. The whole second equation becomes your second row, and the third equation becomes your third row. Sometimes with these matrices you'll see a vertical line like this that separates all the variable coefficients with the constants on the other side of that equals. This is always assumed to be the x coefficients in this column, the y coefficients in this column, and the z coefficients in this column. Now what are we allowed to do to this matrix? Well, we're allowed to do to this matrix exactly all the things we would be allowed to do to this system. So you're allowed to multiply an entire equation by a constant, so that means we're allowed to multiply an entire row by a constant. That's this operation number 2. We're allowed to move equations around. It doesn't matter which equation is listed first. I could put this bottom one up here on top and swap positions. So you're allowed to do that with rows as well. You're allowed to swap or interchange 2 rows. And then the last thing that we do here is like that 2-step process that we do when we try to eliminate x's. If I wanted to eliminate this x right here, I could multiply this entire row by -2 and then add it to the second equation so that the x's would cancel out. And so that's what this step right here is saying we can do. We can multiply an entire row by any number and then add that result to another row. These are called your elementary row operations, and these are basically the rules that you are to follow when you're trying to convert a matrix into our triangular form. To solve a system of linear equations using its augmented matrix, we use these elementary row operations to arrive at our triangular matrix. This is called row echelon form, or REF. And this method is often referred to as Gaussian elimination. For a 3 by 3 system, this is typically what it would look like in triangular form. You would want to see ones along the diagonal, zeros below the diagonal, and any number whatsoever above the diagonal and to the right of that line. So you want ones along the diagonal and zeros below. So this is called row echelon form, and we want that first number in each row to be a 1. This is called the leading entry. The leading entry in each row is to the right of the leading entry in the row immediately above it, which basically just means you want ones along that diagonal. And then all the rows that might have zeros, all zeros, are always at the bottom of the matrix. So occasionally in higher systems or more complicated problems, you might have additional rows down here with all zeros. And if you have any of those all zero rows, we always put those at the bottom of our matrix. So this is called row echelon form, and this would be an example of a matrix in that row echelon form. You've got your ones along your diagonal, you've got your zeros below, and then any zero rows all the way at the bottom. Reduced row echelon form, called RREF, looks very similar, but this time you have ones along your diagonal and zeros below, just like we would with row echelon form, but we also have zeros above the diagonal as well. So you have ones all the way along the diagonal and zeros everywhere else except for on the other side of that bar, on the other side of that equal sign. Those can be any numbers whatsoever. And if you have any zero rows, then they again would be all the way down at the bottom. Okay, so this is called reduced row echelon form. So this would be an example of a reduced row echelon form. Ones all along the diagonal, zeros below and zeros above, and then you have your numbers off to the right. And the process of taking a matrix and turning it into this reduced row echelon form is called the Gauss-Jordan elimination. So let's practice this. We're going to just do one of these by hand just to kind of review the process, and then I'm going to show you how to do it on your matrix. So depending on your instructor, you may be asked to do some of these by hand, but presumably most of them you'll be able to do using your calculator. So let's take our system that we have right here, and the first thing that we are going to do is we're going to turn it into a matrix, that augmented matrix. So each equation becomes a row using just the coefficients. So this top equation, I'm just going to use the 4, the 8, the -4, and then on the other side of that line I'm going to put a 4. And I like to use that vertical line to separate where my variable terms are and where my constants are. You don't have to use that vertical line if you don't want to. The second equation gives me a 3, a 6, a 5, and a -13. And the last equation is a -2, a 1, a 12, and a -17. Now I want you to notice something. This is what we call a 3 by 3 system because it had 3 equations and 3 variables, x, y, and z. But the matrix that we actually created here has 3 rows, but it has 4 columns because we get an extra column for those constants. So this is actually a 3 by 4 matrix. So when I show you in a little bit how to type this into your calculator, you want to make sure that you're using a 3 by 4 matrix. Now what we're trying to do is turn this into that row reduced echelon form. So I want to try to get ones along the diagonal and zeros below. And we're going to just do row echelon form first, which is just the zeros below the diagonal, And then eventually we'll convert that to row reduced echelon form, which also has the zeros up above. Okay? Now here's my suggestions when you're doing this by hand. Always try to get the 1 in that upper left column first. If you can get that to be a 1, then you want to be able, and you'll always be able, to get these zeros below in your next 2 steps. So get this first column completely in the form that you want it to be in. Then you're going to get that 1 in the middle next, which is sometimes the hardest part of the whole matrix. Once you get that to be a 1, then you will be able to get the 0 below it. So this column will be done. And then finally you'll always be able to get that last number to be a 1 last. And this is the steps that you would take for that row echelon form. Not for reduced row echelon form, but just for row echelon form. And I'll show you how to do the reduced one in just a little bit. So our first goal is to try and make this first entry right here a 1, if at all possible. If you have any 1s in this first column, then it would be easy to just swap rows and make that 1 go up to the top. Unfortunately, none of these coefficients of x's were 1s, so that's not going to be a simple fix. But, and this is something you always want to look for, look across this entire first row. Every number there is divisible by 4. If we divide this entire row 1 by 4, that's going to turn this 4 into a 1, and it's going to make these numbers get smaller, which is always a good thing. So that's what I'm going to do for my first step. I'm going to divide this entire first row by 4. So it turns into a 1, a 2, a -1, and a 1. And I'm not doing anything yet to row 2 or row 3. Now that you have your 1, you'll always be able to get the 2 zeros below it by doing this 2-step process. Say we want to get rid of this 3 and turn it into a 0. So this is how you do that. You take your row 1 and you always multiply it by the opposite of the number you're trying to get rid of. So I'm trying to get rid of 3, so I'm going to multiply by a -3. That's step 1. Once I get that result, I'm going to add that back in to row 2 to cancel out these 3's and -3's. Now this is kind of tricky to do in your head, so what I like to do is I like to break it up, and first I'm going to write little tiny numbers in the corners here that represent this entire top row times a -3. So this would become a -3, this would be a -6, +3, and this would be -3. And then what I'm going to do is I'm going to add that result down to row 2. So my answer needs to go in row 2. What do I want in row 1? Remember, we want that 1 in the upper left corner, so keep the original row 1 with the 1 in that left corner. Don't use the little black numbers that I have up here. Use the 1. Keep that. You don't want to lose it. In row 2, we're going to put the answer that we get when we add these 2 rows together. So -3 plus 3 is 0, -6 plus 6 is 0, 3 plus 5 is 8, and -3 plus -13 is -16. I haven't done anything to row 3 yet, so it stays the same. Okay, we got our first 0. Now we want to get this last row to have a 0 in the left column. So I'm going to do exactly the same steps that I just did, but this time I want to multiply row 1 by the opposite of the number we're trying to get rid of. So this time I'm going to want to multiply by +2, and I'm going to add that result down to row 3. So first let's double everything in this first row. So this becomes 2, 4, -2, and 2. And then I'm going to add that down to row 3. Keep the original row 1. Keep row 2, because we're not working with that at the moment. Put the answer in row 3. So 2 plus -2 is 0. 4 plus 1 is 5. -2 plus 12 is 10. And 2 plus -17 is -15. Okay, now that we have our 1, 0, 0, that first column is done. So our next strategy is to try and get a 1 in the middle and a 0 below it. Now, before we work on that, I want you to look at a couple of things here. This should be striking you as something that we could reduce. If you look at row 2, everything in that row 2 is divisible by 8, and everything in row 3 is divisible by 5. So I always take advantage of that. If you have an entire row that's divisible by a common factor, I always like to divide through by it because it just makes the numbers get smaller and easier to manage. So I am going to take row 2 and I'm going to divide it by 8. And at the same time, just to save myself some writing, I'm going to take row 3 and divide it by 5. So let's write out what that turns into. So we're not doing anything to row 1. Row 2 becomes 0, 0, 1, negative 2, and row 3 becomes 0, 1, 2, negative 3. Now, this is where you want to look. We want to get a 1 in the middle and a 0 below it. Well, that's what we have, but it's backwards. So here's where we can do that simple swap of two rows. We're just going to swap row 2 and row 3. Now, you're not just going to swap these two numbers. You're going to swap the entire row 2 with the entire row 3. So it's going to turn into row 1 staying the same, and instead of row 2, I'm going to now put row 3 in the middle, and I'm going to put this row 2 down on the bottom. And that's actually excellent for us because not only did I get my 1 and my 0 in the middle that I wanted, but I also got a 1 on the corner here. So I have my entire diagonal being 1s, and I have my 0s to the left. So this is what we call row echelon form. Now let's find reduced row echelon form, which means making all these numbers above the diagonal become zeros. So here's how you can do that. This time, instead of starting at the top one and working our way down, we're going to start at the bottom and work our way up. So if we have a 1 in this bottom right corner, I am going to use it to turn these two guys into zeros. So to do that, I'm going to take this entire row 3, and I want to use that 1 to get rid of this 2. So I'm going to multiply by its opposite, negative 2, and I'm going to add that result to row 2. Now multiplying this entire row 3 by negative 2 keeps these zeros and turns this into a negative 2 and turns this into a 4. And now we're going to add that up to row 2. So here's what my matrix becomes. 0, 0, 1, negative 2 stays in the bottom. We don't want to lose that 1. But now in the middle, this becomes 0 plus 0 is 0. 0 plus 1 stays 1. Negative 2 plus 2 is 0. And 4 plus that negative 3 becomes a 1. And I haven't done anything to row 1 yet. So now I have a 0 right here. Last thing I want to do to finish off this column here is turn this negative 1 into a 0. So the way I'm going to do that is just like what I did before. I'm going to use this 1 and this negative 1 and try to cancel them out to get my 0. And on this particular example, they're already opposites, so we don't even need to multiply row 3 by anything. We can just go ahead and take row 3 and add it to row 1. So we're adding together row 1 and row 3. So let's see what that would give me. We're putting our answer in row 1. So 0 plus 1 is 1. 0 plus 2 stays 2. 1 plus negative 1 becomes a 0. Negative 2 plus 1 becomes negative 1. I'm not doing anything to row 2, and I'm not doing anything to row 3. Alright, we have our two zeros here. We're almost done. All I need to do now is get rid of this 2 and turn it into a 0. So how am I going to do that? Well, to turn this into a 0, I'm going to need to use this 1 that's below it. So we're going to multiply row 2 by the opposite of this number that we're trying to get rid of. I want to get rid of 2, so I'm going to multiply by negative 2. So this will stay 0. This will become a negative 2. This will stay 0. And 1 times negative 2 is negative 2. And now we're going to add those little numbers back into row 1. So my final matrix here, 0 plus 1 stays 1. Negative 2 plus 2 becomes a 0. 0 plus 0 stays 0. Negative 2 plus negative 1 is negative 3. I'm leaving row 2 the way it was, and I'm leaving row 3 the way it was. So now we have 1s along the diagonal, 0s below, and 0s above. So this is called reduced row echelon form. And the reason we like reduced row echelon form so much is because it tells us our answers. Remember, this first column is your x coefficients, this second column are your y coefficients, and this third column is your z coefficients. So look at that top row. What does it tell us? It tells us that x, and no y's or z's, must be negative 3. If you look at row 2, no x's and no z's, but y has to be 1. And row 3 tells me that z has to be negative 2. So my solution must be negative 3, comma 1, comma negative 2. So just by getting it into that reduced row echelon form, all the numbers over here on the right are your answers. Okay, now what I'm going to do is I'm going to show you how to do all of these same steps on your calculator. So let's go back up here so we can see what our original system was, and we're going to need to pull up our calculator and type it in. So on your calculator, what you want to be looking for is the matrix button, which is right above x to the negative 1, right here in blue. So in order to access the matrices capabilities on your calculator, you're going to need to press second x to the negative 1. And this is what you should see. There's 3 different things up here across the top. The names here, this just enables you to access any matrix. Matrix A, matrix B, and so forth. If we arrow over to the right, the math commands enable you to do stuff with your matrix, and if you arrow down here, keep going past number 7, keep going, you'll see for letter A and letter B, there's that that row echelon form, which is the REF, and the reduced row echelon form, which is that RREF. So that's where we're going to access those commands. But before we can use those, we need to edit our matrix and create our matrix. So I want to arrow across to the top where it says edit, and it looks just like the initial screen we saw when we clicked on matrix, but now the edit is highlighted. And if I hit enter, it's going to allow me to edit matrix A. So I'm going to hit enter. And you may or may not have something already typed in your matrix. That's kind of up to you. So what we want to do here is remember that our matrix that we want to type in, remember it was a 3 by 4 matrix. We're going to have 3 rows, 1 for each equation, but we need 4 columns, 1 for the x's, 1 for the y's, 1 for the z's, and 1 for the columns. So we need to adjust this and make the dimensions, instead of being a 1 by 1, we need to change that to 3 by 4. So just type in where that 1 is, a 3, and then click to the right and change that 1 there to a 4. And if you hit enter, it now creates a matrix that has positions for 3 rows and 4 columns. And now what we need to do is type in what our numbers are. And this comes straight from the system. So our first row was 4, hit enter, then 8, hit enter, negative 4, hit enter, and then 4. Whoops, I must have clicked on something wrong. Let's go back and edit this matrix A. So I'm going to go to edit, hit enter, and let's go 4, 8, and then this is supposed to be a negative 4, hit enter, and then positive 4, hit enter, and it'll now move you to row 2. So we want a 3, a 6, a 5, and a negative 13. And now I'm into row 3, and I want a negative 2, a 1, a 12, and a negative 17. Okay, now matrix A has just been edited and created. So now you're going to go back to your home screen. So just quit out of here. And you want to start in your home screen so that you can see the different results of what you're going to do. So from your home screen, now click on matrix again. So second x to the negative 1. And this time we're going to go over to math, and we're going to turn our matrix into those echelon forms. So let's do our row echelon form first, REF. So that's option A here. Hit enter, and you need to tell it which matrix you want it to turn into row echelon form. So we have to go back to matrix again and get matrix A. So that's what this names is for. So once you get to matrix, your number 1 on A is already highlighted. So just hit enter and it'll paste matrix A into those parentheses. Close the parentheses, hit enter, and here's what the row echelon form is for matrix A without you having to do any of the work. Really nice, right? Saves you a lot of time and energy. So now let's do that all over again, but this time let's do the row reduced echelon form. So from my home screen, I'm going to click on matrix again, and I'm going to go over to math, and I'm going to arrow down until I get to RREF. Hit enter, and now you need to tell it which matrix to do this on again. So we're going to go back to second matrix, and I still want to do it on matrix A, which is the one that's highlighted. So just hit enter, close your parentheses, and here is the row reduced echelon form with all those ones along the diagonal, zeros below and zeros above. So the solution to our system is just these numbers on the right side. So x is negative 3, y is 1, and z is negative 2. So using the calculator is a super quick, easy way to get your answer into these nice triangular forms. Okay, let's look at the next problem here. So one of the things that we're going to explore a little bit more now that we have this technology is what to do when you have a dependent system or an inconsistent system. So those special cases. So for example, a system which has no solution, which is what we call inconsistent, has a reduced row echelon form similar to the following. And remember, there's kind of this implied line right here. These are your x's, your y's, and your z's. So this is a 3 by 3 system, 3 equations, 3 rows, and 3 variables. But if you look at that bottom row, what is that bottom row trying to tell us? It's saying that there's 0 x's, 0 y's, and 0 z's. So that's just 0. And what is it supposed to be equal to? It's supposed to be equal to 1. And we know that 0 does not equal to 1. So what you'll see with an inconsistent matrix is that you'll have zeros to the left and you'll have a non-zero to the right. So you'll get no variables at all equal to some non-zero constant, which is a false statement. And so that's the clue that this is going to have no solution. So look for zeros along the bottom to the left of your line and a non-zero to the right. So that's if it's inconsistent. The other special case that we sometimes see are solutions that are consistent but that are dependent. So these are, in a 2 by 2 case, this would be like coinciding lines, or in a 3 by 3 case, coinciding planes, or something similar to that. So let's look at the 2 possible ways that you might see a dependent system. Here's the first case. We say that a system which has an infinite number of solutions, so that it's considered dependent, will have a reduced row echelon form similar to either this case or the next one. So here's case 1. In case 1, what we have are 4 variables. X is column 1, Y is column 2, Z is column 3, and W is column 4, and that vertical line would be right here. So this is really a system with 4 variables. But how many equations are there? Since there's only 3 rows, this is trying to have a 4 variable system with only 3 equations. And usually what that implies is there may not be enough information to actually solve it completely. And that's why it's going to become independent. So look at what we have here. We've got a 1, a 1, a 1 along that diagonal, but there's no 4th row to tell us what W is. Okay, so let's see how we're going to write out our solution. To get our solution, we're going to look at each of these rows and write down what they would imply. Let's start at the bottom and work our way up. So what does this bottom row right here tell us? Well, there's no X's, there's no Y's, there's 1 Z, and there's 3 W's, and that's supposed to equal to 0. So that's the bottom row. Let's move up a row, and what does this middle row tell us? No X's, 1 Y, no Z's, no W's, and that's supposed to equal to 5. So at least we know exactly what Y should be. If we move up to the top row, that tells me that 1 X plus no Y's and no Z's, but a minus 4 W is supposed to equal to 0. Now what I like to do is I like to solve these two right here in terms of Z and X. So this one I'm going to solve it for Z by subtracting that 3W over to the other side. And on the bottom one here, I'm going to solve for X by adding that 4W to the other side. And this is how we're going to write our answer. Our answer in curly braces is going to be the set of points of the form X, comma Y, comma Z, comma W, such that X is equal to 4W, Y is equal to 5, Z is equal to negative 3W, and what's W equal to? Well, W is any real number. There was no restriction on what W had to be. So that's why this is called a dependent system, because the answer depends on what you choose for W. X is determined by whatever W is, Z is determined by whatever W is. Y was the only number that was fixed. So this is case 1, when you tend to have more variables than you have equations, so it becomes a dependent system because you don't have enough information. The other case that you might see for a dependent system would look like this, where still there's an X, a Y, a Z, and a W. So here we still have those 4 W's, or excuse me, those 4 variables. But look at this bottom row. This bottom row is all zeros to the left of the line, but it's also 0 to the right of the line. And if you look at that bottom row, that's saying 0 equals 0, which is a true statement. And so that's how you know that this is that dependent case again. How do we write our solution when you have zeros to the left and zeros to the right? Just like what we did in the last example, we're going to go row by row. This bottom row doesn't really tell us any restrictions at all because it's always true. What does the middle row tell us? It tells us no X's, 1 Y, no Z's, no W's, and Y has to be 5. The top row tells me that I need 1 X, a minus 3Z, a minus 4W, and that's supposed to equal 0. And what I like to do is solve this for X. Since X has that coefficient of 1, I can just add the 3Z plus the 4W over to the other side. Now here's how we're going to write our answer. Curly brace, X, comma Y, comma Z, comma W. And then what is X supposed to be? Well, in terms of the other two, X is 3Z plus 4W. What's Y? I knew Y was 5. What's Z? There wasn't any restriction on Z. And what's W? There was no restriction on W over here either. So Z and W can be any real number. So X depends on both Z and W. Whatever you choose for Z and W, that determines X. So you're going to have a dependent system if you have fewer equations than variables, or if that bottom row gives you all zeros to the left of the line and all zeros to the right of the line. Okay, let's try another system here, and again we're going to use our calculator to help us out. So the first thing we're going to need to do is turn this into our matrix, and we know that this top equation gives me 6, -1, -1, and then that 4, -12, 2, 2, -8, 5, 1, -1, and 3. So this is 3 rows and 4 columns. So we need a 3 by 4 matrix. And I'm going to let you use your calculator to figure out what that reduced row echelon form is. So let's pull up the calculator and then type in our new matrix. So I'm going to clear out my home screen here, and I'm going to go to matrix, so second, x to the -1, and we need to edit matrix A and type in the new numbers that we want to use. So hit enter, and we still want a 3 by 4 matrix, so I don't need to change that, but I do need to type in my new numbers. So I want a 6, I want a -1, another -1, and a 4. And then in row 2 I want a -12, a 2, another 2, and a -8. And in row 3 I want a 5, a 1, a -1, and a 3. So now matrix A has been typed in. We're going to go back to our home screen, so quit out of here, and then once you are back in your home screen, we're going to go to matrix, so second x to the -1, and we're going to go over to math, scroll down until we get to RREF, reduced row echelon form, and hit enter. And I want to use this on matrix A, so we're going to hit matrix again and just click on 1 or hit enter right here, and it'll paste in matrix A, close the parentheses, and hit enter. Now notice on this one we are getting some decimals, so what I want to show you is how you can turn these into fractions very easily on a graphing calculator like this. If you go to math, right there at the top is this frac command, and what it does is it takes any decimal that is in the last entry and it turns it into its fraction equivalent. So if we just hit enter, it's going to take our last answer, which was that matrix, and put everything in terms of fraction form if possible. So this is what it looks like. 1, 1, 0 along that bottom row, -2 11ths, 7 11ths, and if you arrow over to the right, you can see the rest of those elements if they go off of your screen. So just hit your left or your right arrow to see all of those entries. So let me copy this matrix down on our notes, and then we'll evaluate what it's telling us. So just a little note here, you can use that frac command if needed. And this is what our reduced row echelon form matrix turned out to be. It was a 1, 0, -2 11ths, and then a 7 11ths, 0, 1, -1 11ths, -2 11ths, and then 0, 0, 0, 0. Here's that imaginary line if you need to draw it in. Notice this isn't what we would normally think of as reduced row echelon form, because I don't have zeros all above that diagonal of 1. But the reason why is because I don't have that full diagonal of 1. Look at that bottom row. You have all zeros to the left and you have a 0 to the right. So that implies that this is going to be a dependent system. There's not enough information to get an exact solution, just an ordered triple. So how are we going to write out our answer? Well, we need to use these two rows to help us. This middle row, remember this is x, y, and z, tells me that I have no x's, but I have one y minus a 1/11th z, and that's supposed to equal negative 2/11ths. If you solve that for y, by adding that 1/11th z over to the other side, that tells me what y needs to be when I list out my final solution. Let's go to the top row. This says that x minus a 2/11ths z is supposed to equal 7/11ths. Let's solve that for x by adding 2/11ths z over to the other side, and now I know what x needs to be. So this is how I like to write my solution. Parentheses, the only variables we have are x, y, and z. There's no w on this problem because there's only the 3 columns here for our variables. The x is supposed to be 2/11ths z plus 7/11ths. The y is supposed to be 1/11ths z minus 2/11ths, and there was no information about z, so z can be any real number. So this is dependent because x and y depend on what we choose for z. Okay, let's try the next one here. Let's write out our matrix first. This time we have row 1 becomes 1, negative 2, 1, and then that 0. 2, 2, negative 3, negative 3. There's no x in this third equation, so it has a 0. 1 for y, negative 1 for z, and then a negative 1. And this is a negative 1, a 4, a 2, and a 13. Here's your x's, your y's, and your z's. Now what size matrix did this turn out to be? We have how many rows? 4 rows. And how many columns? 4 columns. So when we edit our matrix, we're going to need to use new dimensions here. We need a 4 by 4 matrix. But look at your system here. How many variables were there? There were only 3 variables because we only had x, y, and z as our unknowns. But how many equations were there? 1, 2, 3, 4. So sometimes when you have a problem like this, there may be a solution or there may be some problems because you kind of have only 3 variables but 4 restrictions on those variables. So there's kind of too much information instead of too little information. So we're going to see what happens with this situation. So the first thing we're going to do is get our calculator out and type in this new matrix for matrix A. So let me clear out my home screen, and then I'm going to go to Matrix, and I'm going to go over to Edit, and we need to change our dimensions here because this time it's a 4 by 4 matrix, and row 1 is going to be 1, negative 2, 1, 0. Row 2 is 2, 2, negative 3, negative 3. Row 3 is 0, 1, negative 1, negative 1. And row 4 is negative 1, 4, 2, and 13. Okay, matrix A is in. Let's quit and go to our home screen, and then I'm going to click on matrix and go over to math and arrow down to that RREF, row reduced echelon form. Hit enter, and we want to do it on matrix A, so I'm going to hit matrix again and just click on matrix A, number 1. Close the parentheses, and here's what we get. Okay, so 1, 0, 0, 1, 0, 1, 0, 2, 0, 0, 1, 3, and notice that bottom row is all zeros, so that would normally imply that we are dependent, but because this was only a 3-variable problem instead of a 4-variable problem, that was just kind of an extra row with extra information that didn't contribute to anything in terms of the final solution. Look at what the first 3 rows are telling us. This bottom row, the third row is telling me that z is 3. The second row is telling me that y is 2. And the first row is telling me that x is 1. So we are able to just get a unique solution here. X is 1, y is 2, z is 3. So let's write that down. So the reduced row echelon form turned out to be 1 0 0 1 0 1 0 2 0 0 1 3, and then that bottom row was just all zeros. So that told us that x was 1, y was 2, and z was 3. So there's our final solution. Okay, we're going to finish up with just a couple of word problems here. Number 7 says that Carletta has $10,000 to invest. As her financial consultant, you recommend that she invest in treasury bills that yield 6%, treasury bonds that yield 7%, and corporate bonds that yield 8%. Carletta wants to have an annual income of $680, and the amount invested in the corporate bonds must be half that invested in the treasury bills. Find the amount in each investment. So we've got our treasury bills, which are yielding 6%. We have our treasury bonds, which are yielding 7%. And we have our corporate bonds, which are yielding 8%. Let's say that she invests X amount at 6%, Y amount at 7%, and Z amount at 8%. What we want to do is, out of this word problem, create a system. So we need 3 equations because we have 3 variables if there's any hope of getting a final solution here. So what's one thing that we know? Well, the very first sentence tells us that she has $10,000 to invest. How much is she investing in each? X, Y, and Z. So the total investment is however much X she puts in, plus however much Y she invests, plus however much Z she invests, and that can't total anything more than $10,000. So there's equation 1. And that doesn't have anything to do with the percents. It's just based on the actual amount of money that she has to invest. Equation 2 will involve these percents because it's going to use this annual income of $680. That's like your interest earned. How do you find interest? You take your interest rate, which are these different percents, turn them into decimals first, and then you just multiply that interest rate times the amount of money that you've invested. So we're going to take 0.06 times X. And then we're going to take 0.07 times Y and 0.08 times Z. And all 3 of those interest amounts have to total her annual interest of $680. So there's our equation 2. We need one more equation if we want to be able to get a solution here. And it tells us that the amount invested in the corporate bonds, which is what we're calling Z, must be half that invested in the treasury bills, which is what we're calling X. So the amount invested in corporate bonds, which is our Z, must equal half that invested at the treasury bills, which is our X. Notice I'm not using my percents at all. I'm just referring to the amount invested, which is just the variable by itself. It's not referring to the interest earned, just the amount invested. Now, to make this bottom equation line up nicely, you probably will want to subtract that 1/2 X over to the left side, and therefore you'll have a 0 on the right side. And this Z is a positive Z. So now all my X's, Y's, and Z's are all lined up. So this is going to become the matrix 1, 1, 1, 10,000, 0.06, 0.07, 0.08, 680. Since I'm using decimals there, I'm going to go ahead and use a decimal for this negative 1/2. So negative 0.5. There's no y in that third equation, so it's a 0, and then a 1, and then that's equal to 0. This has 3 rows and 4 columns, so it's a 3 by 4 matrix. So this is what we're going to type into our calculator for matrix A. So clear this out, and then let's go to matrix, and I'm going to edit, and I want it to be a 3 by 4 matrix, and I want 1, 1, 1, 10,000. And then I want 0.06, 0.07, 0.08, 680, and then finally negative 0.5, 0, 1, 0. Okay, so matrix A is in. Let's quit and go to our home screen, and then we're going to hit matrix. We're going to go over to math, and we're going to arrow down to our reduced row echelon form, and we want to do it on matrix A. And you can imagine with all those decimals in there, this is definitely not something you'd want to do by hand. So here's our reduced row echelon matrix. Nice triangular form, zeros below and zeros above, so these numbers on the right side are exactly what my solutions are. So x is 4,000, y is 4,000, and z is 2,000. So let's write that down. So we get 1, 0, 0, 4,000, 0, 1, 0, 4,000, and 0, 0, 1, 2,000. So this is x, this is y, this is z, and remember that the x was our treasury bills, so we want to invest $4,000 in there. Y was our treasury bonds, so we want to invest $4,000 in there, and z was our corporate bonds, so we want to invest $2,000 in there. Okay, last example. Here is a very common type of problem that you see with these matrices, and you can probably infer the implications here for real life situations. This is talking about traffic flow in a section of the city. So here's a little map that indicates one-way streets. We've got First Street going to the right, and then we've got this other street going to the left. It's hard to read for me here. Second Street going to the left. This is Avocado, and then this is Birch. So we have these arrows that represent the flow of traffic. The numbers on the diagram show how many cars enter or leave this section of the city via the indicated street in a certain 1 hour period. So this would say we have 180 cars coming into this intersection in 1 hour. The variables x, y, z, and w represent the number of cars that travel along the portions of First, Second, Avocado, and Birch streets during that period. We want to find out how many cars go through those streets, assuming that none of the cars stop or park on any of the streets. They just keep moving through these intersections. So this is a traffic flow problem, and a good way to help organize how you're going to set this problem up is to label your 4 different intersections. We have an intersection here, which I'm going to call A, an intersection here B, an intersection here C, and an intersection here D. And what we need to maintain the traffic flow and not have kind of a pileup of cars is we want the number of cars going into that intersection to equal the number of cars going out. So whatever comes in also has to go out at these intersections. So let's see if we can come up with what our different equations are going to be. So we want the in cars to equal the out cars. So at intersection A, what's coming into this intersection? What arrows are pointing in? We have this 200 going in and this 180 going in. So there's 200 cars plus 180 cars going in to intersection A. What's going out of it? X is going to the right and Z is going down. So X plus Z is coming out. If we clean that up just a little bit, I'm going to put the X plus the Z on the left side, and 200 plus 180 becomes 380. So there's our first equation in our system. We have 4 variables here, X, Y, Z, and W, so we're going to need 4 equations, which we'll be able to do because we've got 4 different intersections. So let's look at intersection B. What's going in to B? Well, we have a 70 going in to it, plus we have this X going into B. So 70 plus X is going in. What's going out of B? We have 20 going out, and we have a W going out. So I'm going to try and get my variables on the left side over here just to make this a little bit cleaner looking. So this is going to become X. I'm going to subtract the W over to the left side, and I'm going to subtract the 70 over to the right side so that the numbers are on the right. So this becomes X minus W equals negative 50. Okay, there's equation 2. Now let's do equation 3 for intersection C. What's coming into C? Well, we have W coming into C, and we have this 200 going into C. What's leaving C? 30 is coming out, and Y is coming out. So this becomes, if I move that Y over to the left side by subtracting it, we get a negative Y plus a W, and then I'm going to subtract the 200 over to the right side, and that's going to give me negative 170. Okay, let's do intersection D. What's going into D? Z is going into D, and Y is going into D. So Z plus Y is going in. What's coming out? 200 and 400. So this tells me that I have Z plus Y equals 600. So I have 4 equations. What I want to make sure of is that they're all lined up nicely. So I'm going to do a little writing here. We've got our 4 variables, and then we have our constant over here. So this first equation is an X plus a Z equals 380. The second equation here is an X, a minus W, and a negative 50. The third equation is a minus Y, a plus W, and a negative 170. And our fourth equation, I have a plus Z, I have a plus Y, and that's equal to 600. You want to just make sure that your X's are lined up, your Y's are lined up, your Z's are lined up, and your W's are lined up. Otherwise, your matrix is going to be out of order. So what does this matrix become? Well, this top row right here, these are what I'm looking at. This becomes a 1 for X, a 0 for Y, a 1 for Z, a 0 for W, and I have that 380. Second equation, I have a 1 for X, a 0 for Y and Z, and a negative 1 for W, and a negative 50. Third equation has no X, a minus 1 for Y, no Z, a plus 1 for W, and a negative 170. And the bottom equation, no X, 1 Y, 1 Z, no W, 600. So this is what we need to type in for our matrix A. So let's pull up the calculator. So we're going to click on Matrix, and we're going to go over to Edit. And I forgot to mention over here, what size is this matrix? We have 4 rows, 1, 2, 3, 4 going across, but we have 5 columns. So this needs to be a 4 by 5 matrix. So we're going to need to adjust our dimensions here. We want a 4 by 5 matrix. So it's 1, 0, 0, -1, -50. Then it's 0, 1, 0, -1, whoops, I think I'm looking at the wrong page. Let me try this again. Sorry about that. Let's go back to matrix, and I was looking at the wrong numbers there for a minute. So let me re-enter in here to make sure I'm doing it as we had written down. So we wanted a 1, a 0, a 1, a 0, and we wanted a 380. So that was our first equation. Sorry about that. Second equation, we had a 1, 0, 0, -1, -50. Row 3, 0, -1, 0, 1, -170, and then the final row was 0, 1, 1, 0, 600. So there's our matrix A. Let's quit out of here and then hit matrix, go over to math, arrow down to RREF, and then we want to use matrix A, parentheses, and here's our row reduced form, and I'm going to write this down. Notice that we don't have ones all the way along this diagonal. Look at that bottom row. You've got zeros to the left and a 0 to the right, so this is going to be a dependent matrix. And we don't quite have all those zeros above our diagonal either because it's dependent. So I'm going to copy this down on the next page, and then we'll put our final answer together. Okay, so our reduced row echelon form matrix turned out to be 1, 0, 0, -1, -50, 0, 1, 0, -1, 170, 0, 0, 1, 1, 430, and then that bottom row was all zeros. So that's how we know that it's dependent. If we look at this third row, remember X, Y, Z, and W, this tells me that I need a Z plus a W to equal 430. This second row tells me that I need a Y minus a W to equal 170. And this top row tells me that I need an X minus a W to equal -50. Notice how W is in all three of these. So what we're going to do is we're going to solve X, Y, and Z in terms of W. So Z is 430 minus W. Y is 170 plus W. And X is -50 plus W. So when we write our final solution, we want all the ordered pairs or ordered quadruples here, X, Y, Z, W, where the X is -50 plus W, the Y is 170 plus W, the Z is 430 minus W, and W is any real number. So in terms of this traffic flow problem, W is the key amount. However many cars go through that intersection along that Birch Street, that sort of determines the flow of traffic on the other three streets. So that's kind of the most important piece there. All right, here's our final solution. Okay, that concludes our lecture on more with matrices and the calculator. Good luck.